In this video, we're going to go over the empirical Arrhenius, modified Arrhenius, and Bronsted-Lowry definitions of acids and bases. We're also going to define what conjugate acid-base pairs are, as well as amphiprotic substances. And we're also going to learn how to identify both conjugate acid-base pairs and amphiprotic substances. For the empirical definition of acids and bases, that's based off of properties which can be determined by using our five senses or through experimentation. So the empirical definition of an acid would be that it turns litmus paper red, so you can remember that as red acid if you pronounce the word acid slightly incorrectly. Acids also conduct electricity, they taste sour, and they react to metals to produce hydrogen gas. Whereas for bases, they turn litmus paper blue, so you could remember that B for blue for base. Bases also conduct electricity, they taste bitter, they're slippery, so you could kind of think of soap, right? Soap is a base, and if you put soap in between your fingers, it feels very slippery, and bases do not react with metals. Now, moving on to more theoretical definitions of acids and bases, we're going to start off with Arrhenius theory. So this is based off of, or these definitions are based off of non-observable ideas, but they explain the empirical properties. So with the Arrhenius theory, you could think of that as sort of the original theory of acids and bases. Okay, so the key distinguisher with reactions that explain Arrhenius theory is that the acids and bases, they are by themselves, they're not reacting with anything. And I'm going to put not reacting with water specifically because that is more for modified Arrhenius. But for Arrhenius, the original definition of acids and bases, they are not reacting with water. Okay, so Arrhenius theory states that acids are going to ionize in water to produce hydrogen ions. Okay, and acids, how you can identify them is they either begin with an H or end in COOH. So for hydrochloric acid here, in this reaction, we can see that hydrochloric acid breaks apart. So that's what ionize means. It means that you have a molecular compound that breaks apart into cations and anions that make up the substance. So here we have hydrochloric acid, and the most important part for this definition of Arrhenius theory is that the acids are producing H+ ions. Whereas for bases, they are substances that dissociate in water to produce hydroxide ions. Okay, so bases, typically, not always, but typically they are ionic substances for Arrhenius theory. And dissociate just means, it's a word that's specific for ionic compounds. That just means that it breaks up into its cations and anions. So with this, in our reaction, we see that we have our base sodium hydroxide, and it dissociates into sodium and hydroxide ions. But the key here is that this base is producing hydroxide ions. So again, for Arrhenius theory, acids produce hydrogen, or they ionize to produce hydrogen ions, and bases dissociate to produce hydroxide ions. That's how you can tell the difference between the two here. Okay. However, the problem with Arrhenius theory is that it couldn't explain all acids and bases. So what we did was we modified the definition, so that's how we get modified Arrhenius definitions of acids and bases. So the key difference between Arrhenius, like the original Arrhenius theory, and modified Arrhenius theory is that for modified Arrhenius, we have the acid or the base reacting specifically with water. Okay, so this is going to be one of the definitions that we focus on, modified Arrhenius. The other definition that we're going to focus on in this course is going to be Bronsted-Lowry. So acids, they're going to react with water to produce hydronium ions. So hydronium, that is H3O plus, and it will be aqueous. So how hydronium ions get produced is that the H plus from the acid reacts with water to produce the hydronium ions. So here we have our acid, hydrochloric acid, and it specifically is reacting with water for this to match up with the modified definition of an acid. And you're always going to be producing hydronium for acids with modified Arrhenius definition of acids. Okay, so how this is happening here, how you can visualize it, is that the hydrogen moves from the acid and goes towards the water. Okay, and that's how hydronium gets produced, is that the H plus ion moves from the acid to water to produce hydronium, and then your last product is just what remains from the substance that hydrogen left. Okay, so essentially what you're doing, if you wanted to write it out, right, is you would go hydrochloric acid, but it lost an H plus ion, right? So HCl without the H would just be Cl, and now to deal with the charge, because you need to know what would happen to the charge, this is a neutral compound, so it has a 0 overall charge, right? If it lost a 1 plus charge, right, so if it lost a 1 plus charge, essentially we're going 0 minus 1. That's why the charge on, or that's part of the reason why the charge on the chloride ions is -1. Okay, so for modified Arrhenius reactions, you need to be able to look at the reactants and predict the products. For acids, one of the products is always going to be hydronium ions, and the other product is just going to be your acid with one less hydrogen in it. Okay, and you need to be able to determine the charges. Okay, for determining the charge for hydronium, right, notice with water, it starts out as a neutral charge, but then we added this 1 plus charge. So that's how, so if I wrote this a little bit neatly, it'd just be 0 plus 1. That's why hydronium has a 1 plus charge. Okay, for bases, they react with water to produce hydroxide ions. Okay, so with this, what's happening here is I'm going to write this a little bit different, like the water a little bit different. I'm going to write it as HOH, so there's still 2 hydrogens here and 1 oxygen, It looks a little bit different, but it's still water. So what's happening here is one of the hydrogens is going towards the base. Okay, so one of our products is going to be ammonia with one more hydrogen, so that's an ammonium ion, so NH4. And how we're figuring out the charge here is ammonia has a neutral charge. Since it gained a hydrogen, we go +1, and that's why ammonium has a +1 charge. Now with our other product here, notice here how we started off with water, but then one of the hydrogens moved away to go live with ammonia. So then what we have left over is the hydroxide ion. Now how I'm determining this charge is water starts out as a neutral charge. We lost a +1 charge, so 0 minus 1 is equal to -1. And that's how we get that -1 charge on hydroxide. So again, you need to be able to predict products and charges for your modified Arrhenius equations with both acids and bases. How you can double check yourself is acids are always going to produce hydronium, so H3O plus ions, and bases are always going to produce hydroxide ions. Now, usually students ask me, does it matter which order I put my products in? So could I do it this way or this way? Yeah, you can do it either way with both acids or bases, so long as you are correctly predicting the right products, that's fine. Whether you put the ammonium ion first or the hydroxide ion first for your products, it doesn't really matter. What matters is that you're predicting the correct products. Okay, so one last thing I'm going to write before we move on. I've said this, but I haven't written it out just yet. But with acids, the hydrogen moved away from the acid. So how I like to remember it is acids, think A for away. The hydrogen ion goes away. Now for the bases, notice here that the hydrogen went towards the base. So you can think of it sort of like baseball when your goal is to run towards home base. So bases, so you come towards home base. So what that means is the hydrogen ion moves towards the base. Okay, so another thing that I want to do just before we move on is we're just going to label the acids and bases here. So hydrochloric acid, that was our acid. And in this case, for water, since the hydrogen moved towards the water, even though it's a neutral substance, it acted like it was a base because it accepted the hydrogen. So I'm going to put that in quotation marks because it doesn't have a basic pH, but it was acting like a base. For ammonia, that was our actual base because it does have a basic pH. But for water, since the hydrogen was moving away from it, it acted like it was an acid, even though, again, water is a neutral substance. Okay, moving on to the Bronsted-Lowry concept of acids and bases. Bronsted-Lowry is used for acid-base chemical reactions, which aren't necessarily in solution, so they're not necessarily aqueous, whereas Arrhenius modified is used for acids or bases on their own, but in solution. That's why we write them like reacting with water. It's just because they're in solution and there's a pile of water for the acid or the base to react with. Okay, but for Bronsted-Lowry, you'll often see the acid or base reacting. So for an acid, you will see it reacting with a base. So what I mean by that is something with an acidic pH, so below 7, reacting with something with a basic pH. So that means it's reacting with something that has a pH higher than 7. So that's how you can distinguish Bronsted-Lowry acid-base reactions from modified Arrhenius reactions. Okay, so again, for Bronsted-Lowry acids and bases, typically with these types of reactions, you're not reacting an acid or a base with water, because if you did, that would be modified Arrhenius. Instead, what we're doing for Bronsted-Lowry reactions is we're reacting something with a pH lower than 7 with a substance that has a pH higher than 7. Okay. So for the Bronsted-Lowry, that's what Bl stands for. For the Bronsted-Lowry acid, we're thinking of acids as proton donors. So a proton is just an H+, or an H+ ion. Okay, so we're still operating off of the principle of A for away. Okay, so the hydrogen ion or the proton goes A for away from the acid. Okay, meanwhile, the Bronsted-Lowry definition of a base is that it is a proton acceptor, or it welcomes the H+ ions. Okay, but similarly to what we said for modified Arrhenius, bases, you come towards home base, so the hydrogen ion is moving towards home base. So for our first example here, we have transfer the proton according to the definitions above, then complete the conjugate acid and conjugate base below. All right, so we're starting off with hydrofluoric acid here as obviously our acid, and our base is hydrogen sulfite ions. So if you're wondering how I know the name of some of these here, so with this one, how you can find out the name of that is you can go to your data booklet to page 8 or 9, and you can find the hydrogen sulfate ion. So here, I find it right here. Oh, sorry, that's hydrogen sulfate. We're looking for hydrogen sulfite. So that's going to be right here on page 9, kind of halfway down. So your data booklet does tell you how to name some of these. So you can look it up either here, or if it's a polyatomic ion, then you can also look it up on your periodic table. So where you would find hydrogen sulfite here would be right there. Okay, for naming a compound like this, you'd be using your classical naming or your traditional naming system that was gone over in Chem 20. All right, so we're going to use these definitions where acids A for away, bases go towards home base. Okay, so we're already told hydrofluoric acid, that is our acid. Okay, another way you can tell that it is an acid is, like we said in the previous page, it either begins with an H or ends in COOH. So since this is our acid, A for away, so our hydrogen ion is donated by our acid and accepted by our base. Okay, now for the reaction arrow for this, you may have noticed that earlier we used two different reaction arrows. One was a forward reaction arrow, the other one was an equilibrium arrow. Now, the difference between which one you use depends on if you have either a strong acid or base as one of your reactants. Okay, so for this first one here, because hydrochloric acid is a strong acid, that is why we use the forward reaction arrow, because strong acids or strong bases, they are going to react completely. Whereas with ammonia, this is a weak base. So the reaction with a weak base isn't going to go to completion, so that's why we use these equilibrium arrows. Okay, so let's actually write that as a note just at the bottom of this page. So we're going to use the forward reaction arrow when one of our reactants is either a strong acid or a strong base. We're going to use the equilibrium arrows when one of our reactants is either a weak acid or a weak base. So then the next question is, well, how do I know whether something's a strong acid or a strong base or a weak acid or a weak base? So what you can do is you can go to page 8 or 9 of your data booklet here. So I'm on page 8 right now. And all of these acids above the gray hydronium line, they are all strong acids. Okay, so perchloric acid, where the formula is here, hydroiodic, hydrobromic, hydrochloric, sulfuric acid, and nitric acid, they are all strong acids. Okay, so there's 6 strong acids that you need to be able to find. For the conjugate base formula here, all of these are neutral because the conjugate base of a strong acid is neutral. So all of these here that I've highlighted in pink, these are all neutral. Okay, now the next section, it's below the gray hydronium line. It's actually in between the gray hydronium line and the gray water line. Okay, so in between there, starting at oxalic acid. So actually that's pretty weak. It's hard to see. So starting from oxalic acid and going down to hydrogen phosphate ions. So everything in the acid formula column is a weak acid in between the 2 gray lines. So in between the gray hydronium line and in between the water line, all of those are weak acids. In the conjugate base column, so in this column right here, so that's on page 9, and then going back to page 8, all of these, once again, we're still in between the 2 gray lines. All of these are weak bases. So we'll label that. These are weak bases. And then I'll go back to highlighting in green. So everything that I'm highlighting in green is a weak acid. Anything that I highlighted in this sort of orange color is a weak base. Okay, so in between the 2 gray lines, that's where you're going to find your weak acids or your weak bases. It just depends on which column you're looking at there. Okay. So just to go back to that, you're going to find your weak acids in the acid formula column, and you're going to find your weak bases in the conjugate base formula column. Okay. So now that we know which arrow to use, we're going to look at this. Okay, so hydrofluoric acid, if we go back to our data booklet, hydrofluoric acid is not one of our strong acids. So it's not anywhere where I highlighted in blue. So that means if you can't find it as a strong acid, and if it's not listed in your weak acids, you can assume that it is a weak acid. Okay, and that's just because there's so many weak acids that it's kind of impossible to list them all. So this is a weak acid. And for the hydrogen sulfate or sulfite ion, if we go back, so we found that right here, and we found it in our acid column. But the interesting thing about hydrogen sulfite is you can find it both in the acid column as well as the base column. So let's see if I can find it right there. Now, there is a special name for a substance that you can find both in the acid column as well as the base column. Those are called amphiprotic substances, so that means that they can act either as an acid or a base. We are going to get into that in the notes in a little bit. Okay, but in this case, because the hydrogen sulfite ion could act either as an acid or a base, but hydrofluoric acid can only act as an acid, right? That's how we know that this is a weak base. So because they're both weak, that means we have to use an equilibrium arrow. So actually I'm going to draw this outside of the box. So we'll go like that. Okay. So for this, what we're going to do is I'm going to take the acid, and to predict my product, since one hydrogen ion moved away from the acid, what's left over is a fluoride ion. Okay, so we started out with a neutral compound, so 0. We lost a 1+ ion, so the hydrogen ion. So 0 minus 1 is going to give us -1. That's how we get the charge there. So that is going to be our conjugate base, and I'll explain what conjugates are in a second here. For our other product, we're taking our base, and because we have that one hydrogen that moved in with it, we're going to take this formula and have an additional hydrogen in it. So I'm going to go H2SO3. Now with the charge, we started out with a -1 charge, and we gained that 1+ charge from hydrogen. So that's -1 plus 1, well, that's going to equal 0. So this is why this has a neutral charge. And then I'm going to put the state here. There we go. Okay, so conjugates, you could think of that word as meaning like partners, essentially. So this word kind of means partner. So an acid, its partner is always going to be a conjugate base. For a base, its partner is always going to be a conjugate acid. Okay, so what that means is this conjugate base, this fluoride ion, is the partner to our acid over here, the hydrofluoric acid. And the conjugate acid is the partner to the base. So the base being the hydrogen sulfite ion. So what I'm going to do is I'm just going to color code this. So these two are partners. Same with these two partners. Okay, so for conjugate acid-base pairs, they look very similar, but the only difference is going to be like one will have more hydrogen, one more hydrogen than the other. Okay, so for the next part here, we have that definition. Conjugate acid-base pair is a pair of substances that differ by only one proton. So in other words, one H plus ion. So we got to write out the conjugate acid-base pairs. So for the first one, it's going to be hydrofluoric acid and the fluoride ion. That's the one pair. So again, this is our acid. This is the conjugate base. And then for the other pair, it was hydrogen sulfite ion with sulfurous acid. So the sulfurous acid is the H2SO3. And again, if you're wondering how I figured out the name to this, those were part of the naming rules covered in Chemistry 20, but also you can look up the name. So this substance, H2SO3, is right here. It tells you what the name is right there on page 8 of your data booklet. So this is the base. We know that because it accepted a hydrogen. And this is the conjugate acid. Okay, so the acids will, whether it's just acid or conjugate acid, they will always have one more hydrogen. The bases, whether it's a base or a conjugate base, will always have one less hydrogen. Okay, now something that's important to know here is that, let's say we were talking about H2SO3, so sulfurous acid, and let's say we were talking about a sulfite ion. Okay, so these differ by more than one hydrogen. They differ by 2 hydrogens. So because they differ by 2 hydrogens, that means they cannot be a conjugate acid-base pair because they differ by more than 1 hydrogen. Okay, so I did mention this a little bit earlier on amphiprotic substances. So those are substances that can either act as an acid or a base. So you'll be able to find them both in the acid column as well as the conjugate base column on your data booklet. Okay, so some examples of amphiprotic substances are water. So we saw water acting both as an acid as well as a base on our previous page here. So when it was with hydrochloric acid, it accepted the hydrogen from the acid, whereas when it was with a base, it donated a hydrogen to ammonia. So water, when it acts as a base, then it'll produce hydronium, but when it acts as an acid, so it gives away its hydrogen, it will produce hydroxide ions. For hydrogen sulfate ions, when it acts as a base, so it accepts a hydrogen, we get H2SO4. When it acts as an acid, so it gives away its hydrogen, it will produce SO4 2-. Okay, so again, you need to be able to figure out the charges on any ions here. How I figured it out for the sulfate ion is I said, well, we started off with a -1 charge. I said that it was giving away its hydrogen, so we lost a 1+ charge. So -1 - 1 is equal to -2. That's how I'm getting the charge on sulfate. You can also double check the charge in your periodic table. So since sulfate is a polyatomic ion, you could look it up right there and be like, yep, sulfate ions have a -2 charge. Okay, and then for hydrogen sulfite, when it acts as a base, so it accepts a hydrogen, we get H2SO3 aqueous, and I should have put aqueous on sulfuric acid over here. And then when it acts as an acid, so it gives its hydrogen away, we get SO3 2- aqueous. Okay, so how it's acting, how all of these are acting either as acids or bases is amphiprotic substances. They either donate or can accept a hydrogen. So an amphiprotic substance is a substance that can either donate or accept a hydrogen ion. Actually, I'll just leave it as H+. All right, so we're given these two reactions. Water is behaving as an acid and a base in these two different scenarios here. Okay, so what they've given, because we have substances that are reacting with water, that is your clue that these are modified Arrhenius reactions. So subsequent reactions will mostly be based off of modified Arrhenius reactions or Bronsted-Lowry reactions. So make sure that you're super comfortable with both. So what's happening in this first one here is we have hydrobromic acid, and the hydrogen ion moves away from the acid towards the substance that's acting as our base to give us hydronium ion. So this should be a superscript, and same with this charge on the bromide ion. Okay, so this is our acid, and this is acting like a base, however its pH is neutral. Now for determining the conjugate acid-base pair, so I'm going to look at hydrobromic acid and then I'm going to look at my products. Okay, so the acid and base, they're always on the reactant side of your equation here. the conjugate acid and conjugate base, they're always going to be on the product side. Okay, so I'm looking at our acid, hydrobromic acid, and then I look on the product side and I think to myself, okay, which one of these two products looks most like hydrobromic acid? So obviously it's going to be the bromide ion. So remember, acids are always paired with conjugate bases, so I'm going to abbreviate conjugate base to CB. And with water, I say, okay, well, what on the product side looks most like water? Obviously, it's the hydronium ion. So remember, bases are always paired with conjugate acids. Okay, so what I'm going to do is I'm just going to color code this a little bit. So I'm going to, let's say we use pink. There we go. And then I'll use yellow here. Okay, so what I've highlighted in pink, that's my acid conjugate base pair. And then what I've highlighted in yellow, that's my base conjugate acid pair. Okay, with ammonia, if you look that up on page 8 or 9 of your data booklet. So for ammonia, where you're going to find that is right here. Okay, so since we found it in the conjugate base column, that means it's going to act like a base. So then that means, in this case, water is going to act like an acid even though its pH is neutral. And we need to make some adjustments here. These should be superscript. Okay, so what's happening here is one of the hydrogens is moving away from water towards ammonia. So that's how we get NH4, because ammonia gained one hydrogen, and it's also how we get hydroxide because water lost one hydrogen. So for my conjugate acid-base pair, ammonia, looking on the product side, what looks most like ammonia is NH4. So since ammonia is the base, NH4, or the ammonium ion, has to be the conjugate acid, because a base is always paired with a conjugate acid. And then for water, what looks most like water is the hydroxide ion. So since water is our quote-unquote acid, acids are always paired with conjugate bases. So if I wanted to color code this, we will do our base and our conjugate acid there, and then for our other pair, it'll be water and hydroxide. Okay, so I did say this earlier, I just didn't write it out. The conjugate base is always going to have one less hydrogen than the acid it's paired with. For the conjugate acid, it always has one more hydrogen. Than the base it's paired with. So the terms acid and base, that will always be on the reactant side, whereas conjugate acid, conjugate base, those will always be on the product side. So Ca is just shorthand for conjugate acid, and conjugate base, those are always on the product side. So typically we use modified Arrhenius theory. So when you have an acid or a base specifically reacting with water, so typically we use modified Arrhenius theory when an acid or a base is by itself, and we use Bronsted-Lowry reactions when we have an acid, so something that has a pH lower than 7 reacting with a base, so that's something that has a pH higher than 7. Okay, so example 2, list the acids, bases, conjugate acids, base pairs for the following reaction. Okay, so again, with conjugate acid base pairs, you're just picking what looks similar. So pick what looks similar when comparing reactants with products. Okay, so looking at this reaction here, I'm noticing we have ammonium, which typically acts as an acid, and seeing as like the thing on the product side that looks most similar to it is ammonia. So I see, okay, we started off with 4 hydrogens, we ended up with 3. So that's like my guarantee that I know that a hydrogen is moving away from ammonia, or sorry, from the ammonium ion. Okay, because that's what's going to produce the ammonia. And also, if you look at this hydrogen carbonate ion, in order to create carbonic acid, so H2CO3, the hydrogen carbonate ion had to accept a hydrogen. Okay, so given this, we got to label what is our acid and our base. So this is our acid because it gave away its hydrogen. This is our base because it gained a hydrogen or accepted a hydrogen. Okay, now with figuring out conjugate acid-base pair, we compare what looks similar between reactants and products. So the ammonium ion looks similar to ammonia. So that means that's a pair. So since this is our acid, this has to be the conjugate base. With hydrogen carbonate, what looks similar to it is the carbonic acid. So since hydrogen carbonate ion is the base, this must be the conjugate acid. Okay, so let's fill this out here. So our acids, they are the ammonium ion, and the other acid was our conjugate acid, so carbonic acid. For the bases, that's going to be our hydrogen carbonate ion, so HCO3 1 minus, and then the other base is the conjugate base, so that's ammonia. So the conjugate acid-base pair, so remember these are the partners. So that's going to be, we have ammonium and ammonia. That's one pair. And the hydrogen carbonate ion paired up with carbonic acid. Okay, so just to follow up on how we know, like if you had to write out this reaction, how you would know to use the equilibrium arrow is because both ammonium and hydrogen carbonate are weak acids and weak bases. So you're going to find them between the two gray lines in your data booklet. So if I found them here, let's bring that back. So ammonium is right here. And that's going to be the only place where it shows up. Now, for hydrogen carbonate, we see it here as well as here. Now, since ammonium only shows up in the acid column, that's how you know for sure that hydrogen carbonate is your weak base. But the moral of the story is we use the equilibrium arrow, so this thing, because what's reacting is a weak acid and a weak base. Okay, we would only use the forward reaction arrow if we had either one strong acid or one strong base. How you know your strong acids is that you'll see them listed on page 8. There's one of these 6 acids right at the top here. Okay, with strong bases, those are typically going to be any metal with a hydroxide ion. Okay? All right, which of the following statements are correct for the conjugate base of H2CO3? Okay, so first of all, what is the conjugate base of H2CO3? So remember, conjugate bases, they always have one less hydrogen than the acid. So we just need to take this and subtract one hydrogen. So this brings us back to HCO3, 1 minus. Okay, so this is the substance we're dealing with. So it is amphiprotic. Well, let's go to our data booklet and see if we can find it both in the acid and base column. So I'm finding it right here and right here. So since we found it both in the acid and base column, I agree that it is amphiprotic. Yes, it can act as an acid. Yes, it can act as a base. All right, next one. It can accept 1 proton. So how many protons a substance can accept is usually determined by the charge. Okay, so the charge will tell you how many hydrogens can be accepted here. So let's write some notes here because there's actually a lot that the formula tells you. And I'm going to write it just a little bit lower. So the charge tells you how many hydrogens can be accepted. So your goal is always to get it to be neutral. So if you have a 1 minus charge, you're trying to get it to be neutral. That means this substance can accept 1 hydrogen. Okay, so I also agree with, yeah, it can accept 1 hydrogen. Okay, because what that would do if it did accept 1 hydrogen, that would give us H2CO3. Okay, but Usually substances, like when they have a negative charge and they finally get to a neutral charge, they don't really like going beyond that there. So when it says, can this accept 2 protons, I'm going to say no, because the goal for most substances are to get to a neutral charge, to gain enough hydrogens to get a neutral charge. The exceptions are going to be ammonia, so NH3. NH3 can accept a hydrogen to become an ammonium ion, so NH4 1 plus. The other exception would be water. Water can gain a hydrogen to become hydronium. So those would be the 2 exceptions there. Okay, in terms of losing hydrogens, just while we're talking about gaining or losing hydrogens, how many hydrogens a substance can lose is told to you by how many hydrogens there are in the substance. Okay, so just to finish off talking about amphiprotic substances, just because I didn't mention this, so if hydrogen carbonate acted as a base and accepted a hydrogen, we would get carbonic acid. If it acted like an acid and lost another hydrogen, we would get a carbonate ion. So to finish this question off, I'm saying it cannot accept, so hydrogen carbonate ions cannot accept 2 protons, but it can accept 1, and it is an amphiprotic substance.